Imagine an AI that's capable of, like, writing a flawless 50-page thesis on supply chain logistics in just 3 seconds.
Right, which is pretty much standard now.
Yeah, exactly. I mean, it can parse a decade of your company's financial data, optimize your entire routing schedule, and even draft these, perfectly polite emails to your vendors. It feels like absolute magic.
Oh, absolutely.
But then you ask that exact same superintelligent system to pick up a cardboard box from the floor and just, put it on a desk. And suddenly, it is completely helpless.
It's basically a genius trapped in a box.
Yes. So if you spent the last few years staring at your screen, just amazed by what AI can do, you've probably had this realization. The intelligence we've built is trapped. It has a genius-level brain, but it is stuck inside the digital world.
It's a profound limitation, really. I mean, we have essentially decoupled intelligence from physical agency.
Right.
For all the leaps we've made in, reasoning, coding, generating text, that intelligence cannot tighten a screw. It can't inspect a faulty weld on an assembly line.
And it definitely can't fold my laundry.
Sadly, no. It has no physical body to act upon the world it understands so well.
And that is exactly our mission for this deep dive. We are exploring how AI is finally breaking out of the screen and stepping into the real world. We are pulling from this really fascinating August 2026 article by Shish S. It's titled, Physical AI, Why the Next Chapter of the AI Story Will Be Written in the Real World.
It's a great piece.
It really is. And okay, let's unpack this, because the author isn't just talking about, like, slapping a chatbot onto a Roomba or a factory arm, right? This is a massive convergence of multiple technologies all hitting maturity at exactly the same time.
That's the perfect way to frame it, actually. The author defines physical AI not as just some, evolution of traditional robotics. It's really the collision of four major technological vectors.
Okay, what are those?
So first, you have foundation models, which give AI its reasoning.
Yeah.
Then you have agentic systems, which allow the AI to plan and execute multi-step goals.
Right, the agents.
Exactly. Third, you have high-fidelity simulation, which acts as a training ground. And finally, you have the actual robotics hardware itself.
Wow.
Yeah, and when you bring those four forces together, you create a way for intelligence to finally navigate factories, warehouses, hospitals, farms, and eventually, the very spaces we live in.
So to understand why this shift is so revolutionary, I feel like we first have to talk about how painful it used to be, and honestly still is in a lot of places, like teaching a robot to do literally anything.
Oh, it's incredibly painful.
Because the general public assumes robots are already smart. But historically, they really aren't, are they?
Not at all. Traditional robotics is practically an artisanal, bespoke process.
Artisanal? Really?
Yeah. Let's say you manage a warehouse and you want a robotic arm to, say, move a small metal part from a moving conveyor belt to a static shelf.
Okay, sounds simple enough.
You'd think so, but for decades, deploying that system meant bringing in highly specialized engineering teams for months.
Months, just for moving a part.
Yes. They would use these devices called teach pendants.
Wait, teach pendants? Like a remote control?
Kind of. Think of it as a very complex industrial handheld controller. The engineer actually physically jogs the robotic arm, joint by joint, axis by axis, just to record its exact motion path.
Oh, wow. That sounds tedious.
It is. And then they write proprietary scripting languages to choreograph these millimeter-perfect movements in three-dimensional space.
Was heavily scripted.
Exactly. The system calculates exactly where the X, Y, and Z coordinates of that shelf are, and it moves there blindly every single time.
Which sounds incredibly precise. But if it's moving blindly, I imagine that makes it terrifyingly rigid.
That is the fatal flaw of traditional robotics. It is perfectly precise, but completely brittle. Every single task is hand-coded for a totally static environment.
So what happens if something changes?
Well, if a new, slightly heavier part is introduced on the line, or, if a forklift driver accidentally bumps the shelf and moves it half an inch to the left,
The whole system fails.
the whole system fails. The arm will try to place the part in midair, or it'll just crash straight into the shelf.
Because it doesn't know the shelf is there.
Right. It doesn't actually know a shelf is there. It only knows a mathematical coordinate. So to fix it, you have to halt production and re-engineer the whole system.
That is wild. So if natural language solves their translation problem with computers, the source text points out that foundation models basically flip this entire robotic script upside down.
They really do.
The exact same technology that lets you, chat with an AI assistant on your laptop now lets you converse with a physical machine. The author calls this vibe coding.
Yeah, it's a fascinating term.
It is.
In software development, vibe coding is when you describe the general vibe or intent of an app in plain English, and the AI just writes the underlying code,
Right.
and the author is applying this to the physical world. So instead of writing thousands of lines of motion control code to handle every possible edge case, a developer, or just an operator, can simply state the intent.
Okay, wait, I have to challenge this. You're telling me an operations manager on a warehouse floor, someone with absolutely zero robotics background, can just look at a 500-pound industrial machine and say, hey, pick the damaged items off the line and place them in the reject bin. And the robot just does it.
Essentially, yes.
But that sounds incredibly dangerous. Like, what happens if the AI hallucinates a command and just swings a mechanical arm into a structural pillar?
That is a highly valid concern, and it's exactly why these systems aren't just large language models connected to motors.
Okay, good.
The underlying mechanism here relies on what we call vision language action models, or VLAs. Let's break that down because it explains how we prevent those dangerous hallucinations.
Please do, because going from a spoken sentence to a moving metal arm is a massive leap.
Let's trace the path of your command. First, the model takes in vision, so a camera feed is capturing the conveyor belt. The AI converts that flat video feed into a multidimensional spatial grid. It's identifying objects, calculating depth, and recognizing the physical boundaries of its environment, like those structural pillars you mentioned.
Oh, so it actually sees the room.
Exactly.
Yeah.
Next, it processes language. It takes your verbal command damaged items and maps that concept to the visual data. It understands that damaged means, the boxes with crushed corners.
Okay, so it sees the crushed box, and it knows you want it moved.
Yeah.
But how does it physically do it without a human coding the XYZ coordinates?
That's where the action part of the VLA model comes in. The AI translates that semantic intent directly into joint torque vectors.
Torque vectors.
Yeah, basically it calculates the necessary geometry, the weight of the box, the friction required by the grippers, and it generates a dynamic motion path in real time.
Wow.
In real time.
Right. Because it is relying on its own visual perception rather than a pre-programmed coordinate, it can adapt. So if the box is upside down, it adjusts its grip.
That makes sense. Or if the reject bin was moved 2 feet to the right, the robot simply sees the new location and rushes there instead. It translates human intent into physical execution instantly.
That completely collapses the timeline of innovation. I mean, what used to be a 6-month integration project requiring a whole team of PhDs can now be prototyped in an afternoon.
It's revolutionary.
You have an idea, you describe it to the robot, the AI generates the physical behavior, you test it out, you refine it through conversation, and boom, it's working.
Yeah.
We are taking the pool of people who can program robots from a few thousand specialists to literally anyone who can speak clearly.
Exactly. And it brings us to a massive turning point. But, it also raises a structural dilemma for the industry.
Right. Because if talking to them is so easy, why aren't they everywhere doing my dishes or sweeping every warehouse floor in the world?
That's the big question.
You would naturally assume the robots themselves must cost $1 million. Or maybe the hardware is just too clunky to deploy at scale.
What's fascinating here is that the bottleneck holding us back is not what most people assume. The industry does not have a hardware problem.
Really? Not a hardware problem?
No. Capable, highly affordable hardware exists today, and it is improving rapidly.
Yeah, the text specifically brings up companies like Unitree. I actually looked them up while reading the source material, and they're selling these incredibly agile robotic dogs and even full humanoid robots.
Yeah, they're amazing.
And at price points that are drastically dropping, too, sometimes rivaling the cost of a used car. So if the physical bodies are cheap and ready, what is the holdup?
The holdup is a massive systemic software problem. Robotics today is stuck in a fragmented, siloed state.
How so?
To give you some historical context, it looks a lot like the computing industry before the personal computer came along. It is entirely vertically integrated.
Vertically integrated meaning the hardware manufacturer also forces you to use their specific software.
Precisely. If a company builds a robotic arm, they build their own proprietary operating system to run it.
Right.
So imagine a logistics company buys 3 different robots from 3 different vendors. They buy a robotic arm to pick items, a mobile cart to transport them, and maybe a drone for inventory checks.
Sounds like a standard warehouse upgrade.
Sure, but because of vertical integration, they are effectively running 3 totally incompatible tech stacks. A perception system that learns how to identify a fragile glass bottle on the picking arm cannot share that intelligence with the mobile cart. There is zero shared brain.
Okay, I think I have a way to visualize this for anyone listening. Imagine you want to use a smartphone, but every single app requires you to buy a completely different, physically separate phone.
That's a great analogy.
Right, like you want to check your email. You have
Yeah.
to buy the Apple email phone. You want to check the weather, you put that down and pick up the Samsung weather phone. And none of the phones can talk to each other. They don't share your Wi-Fi password,
Yeah.
and they don't share your contact.
Exactly.
No wonder only giant corporations with massive budgets can afford to deploy robots. The hardware might be cheap, but the integration costs must be astronomical.
Your analogy hits the nail on the head. The lack of interoperability means fleet orchestration is essentially impossible for the average business.
I can imagine.
Every single time a company wants to deploy a new robot, they are starting from scratch. The integration and consulting costs end up being like 5 to 10 times the cost of the actual robotic hardware.
So if the disease is vertical silos, the cure has to be a horizontal layer, like a universal brain that can be decoupled from the body.
And this is the core investment thesis of the article. The defining companies of this new physical AI era are not going to be the hardware manufacturers building the coolest titanium arms.
Right.
The massive value will be captured by the software platforms, the horizontal intelligence layers, that make any robot smarter, regardless of who manufactured the motors.
The historical parallels the author draws here are huge. Decoupling the operating system from the physical hardware is what gave us the PC industry.
Yeah.
Decoupling software applications from local servers is what gave us the cloud. And now, decoupling intelligence from the robot itself is what will create the physical AI industry.
It flips the hardware diversity from a massive liability into an asset. With a horizontal intelligence layer, a business just buys the best physical body for the job.
Right. Need to climb stairs,
Yeah.
buy a quadruped.
Exactly. Need to reach a 30-foot shelf, buy a drone. The platform supplies a common shared brain across all of them. Intelligence developed for one form factor instantly informs the entire fleet.
To prove this isn't just theoretical, the source highlights a specific startup from the Microsoft for Startups Pegasus program. They're called General Robotics.
Right, yeah.
They were founded in 2023 by former Microsoft research veterans, and they're building exactly this, a platform for general-purpose robot intelligence.
Yes, their platform is called GRID, General Robot Intelligence Development. And what makes their approach so effective is that they aren't trying to build one monolithic, giant AI model that tries to learn everything at once.
Okay, so what are they doing?
Instead, they believe general intelligence in the physical world emerges from composing modular AI skills.
Modular skills, like Lego bricks.
Exactly like Lego bricks. Instead of trying to teach a robot a complex, overarching task like make a cup of coffee, you teach it discrete skills.
Oh, I see.
You build a grasping skill, a fluid pouring skill, and an obstacle navigation skill. When you need the robot to make coffee, the platform just snaps those modular skills together. And crucially, General Robotics integrates this platform directly with GitHub Copilot.
Wait, GitHub Copilot? Like the tool software developers already use to write normal code.
The very same.
So a standard web developer can just use the tools they already know to orchestrate physical movement in a factory.
That's the vision. You abstract away the complex physics and motor control. A regular developer just calls upon the grasping skill via Copilot, and the GRED platform handles the physical translation.
But this brings up a massive logistical nightmare in my head.
Oh.
Let's say we have millions of software developers suddenly empowered to write AI skills for robots. How on earth do they practice? Yeah.
You can't just have an intern writing experimental code and immediately pushing it to a $100,000 robotic arm on a crowded factory floor. It would crash into walls, destroy inventory, or worse, hurt a human worker.
You're hitting on the fundamental bottleneck of physical data. In software, if a piece of code fails, you get an error message on a screen.
Right.
In the physical world, if code fails, a robot shatters a windshield. This is why the concept of simulation-first training is absolutely critical to physical AI.
Here's where it gets really interesting, because the author introduces high-fidelity simulation environments like AirGen and NVIDIA Isaac Sim. We are talking about hyper-realistic virtual playgrounds for robots.
Right. Before a robot ever touches the physical world, its AI brain trains inside a virtual environment. Let's clarify a term here, reinforcement learning.
Okay.
In this context, imagine a virtual robot dog trying to learn how to walk on ice. In the simulation, it tries a step, slips, and falls. the AI receives a mathematical penalty.
Makes sense. It adjusts its motor control parameters and tries again. It might fall 10,000 times in a few minutes, but eventually it figures out the exact balance of torque and momentum to stay upright, and it receives a mathematical reward.
So you are compressing years of dangerous, expensive physical trial and error into just a few hours of cheap, safe, synthetic experience running on servers in the cloud.
Precisely. This is called synthetic data generation. Because the real world is messy and data poor, we generate our own training data perfectly inside the simulation.
But for a simulation to be useful, it can't just look pretty like a video game, right? The physics have to be flawless.
Absolutely.
And this is where the author introduces what might be the most mind-bending concept in the whole deep dive spatial world models.
To understand spatial world models, we need to contrast them with large language models, which everyone is familiar with today.
Right, the chatbots.
Yeah. A language model is essentially a highly advanced parrot. It has learned the statistical structure of text, so it can predict which word sounds right next, based on billions of examples. But world models are entirely different.
How so?
They are not learning statistics. They are learning the structural laws of physical reality.
So it's the difference between a parrot and a chess player. The language model is just reacting to the immediate context, but the spatial world model is calculating the physical consequences 3 moves ahead.
Exactly.
It is learning actual physics, geometry, friction, weight distribution.
Yes. It learns concepts like occlusion. If a virtual forklift drives behind a wall, the AI understands the forklift didn't cease to exist. It's just hidden, and it will emerge on the other side at a specific speed.
Oh, wow.
If we connect this to the bigger picture, a spatial world model gives the AI an internal physics engine. It understands that if it pushes a heavy wooden block, it requires more force than pushing a hollow plastic box. It can anticipate the physical consequences of its actions before it ever makes a move.
It is essentially giving a robot common sense.
Yes, exactly.
Like, if I walk up to a table and push a glass of water toward the edge, I know it's going to fall, spill, and shatter. I don't need to physically push 1,000 glasses off a table to learn that lesson because I have a world model in my head.
Right, you understand cause and effect.
Spatial world models give that exact same physical intuition to a machine.
And that predictive intuition solves the generalization problem. A robot with a spatial world model doesn't just memorize the layout of one specific warehouse.
Right, because things change.
Exactly. Because it understands how gravity, space, and objects interact fundamentally, you can move it to a completely new building, assign it a completely different task, and it will adapt immediately.
That's incredible.
Plus, software platforms that build the most accurate spatial world models will compound their advantage rapidly. Because every hour their robots spend in the real world feeds back in to refine that model even further.
Okay, we've covered a lot of ground. We have this brilliant, simulation-trained AI brain. We have affordable physical bodies. We have a horizontal software layer connecting them.
Yep.
How does this actually integrate into a modern business? Because right now, large enterprises already use a lot of AI.
They do, but mostly in the form of digital agentic ecosystems. Let's define agentic systems really quickly.
Sure.
These are AI programs that can act independently to achieve a goal. A business might have a digital agent that manages their inventory databases. Another agent plans the logistics routes. Another agent schedules the human workers.
Basically behind-the-scenes software bots.
Right. These digital agents talk to each other and orchestrate the workflow across the company's software stack seamlessly.
But the catch is, the second something physical needs to be moved, like a box needs to be loaded onto a truck or a part needs to be welded, that beautiful digital symphony hits a brick wall.
It completely stops.
The digital agent has to print out a ticket or send a Slack message and hand the workflow over to a human being. The digital-physical loop is totally broken.
You're hitting on the fundamental friction point of modern logistics.
So what does this all mean? How does physical AI close that loop?
It means that a robot is no longer viewed as this isolated, dumb piece of hardware at the end of the line. In this emerging architecture, a robot is simply an agent that happens to have a body.
Oh, I see.
It becomes a peer in the exact same software ecosystem.
Oh, wow. So the digital agent and the physical agent are actually reasoning together in real time.
Exactly. A customer submits an order online. The digital planning agent receives it and breaks down the objective. A logistics agent calculates the sequencing.
And then?
And then an embodied agent, a physical robotic arm, receives the context, plans its motion using its spatial world model, and carries out the physical steps. And while it's moving, it is constantly reporting its physical state back to the digital agents.
They share context entirely.
They share context. The entire physical factory floor becomes just as programmable and trackable as a cloud software stack.
That completely changes how you evaluate the market for this technology. The author makes a very bold claim here. You cannot measure the market for physical AI by looking at the old robotics industry.
No, you really can't. The traditional robotics industry was artificially constrained by those vertical silos and extreme integration costs we discussed earlier.
Right.
When you decouple intelligence from the physical body, and you make physical movement as easy to program as a web app, the total addressable market is no longer just manufacturing companies that buy robots.
What is it then?
The market becomes the value of physical work itself.
I want everyone listening to just pause and dwell on that for a second. Think about every single thing around you right now. The walls of the room you're in, the desk you're sitting at, the device you are listening to this on.
It's all physical.
Human hands, fueled by human caloric energy and hourly wages, had to extract, build, move, and assemble all of those physical materials. What happens to the global economy when that physical movement becomes a programmable software function?
It changes everything.
When executing a physical task becomes as cheap and scalable as running a Google search, it is a staggering fraction of the global economy.
It truly is. The AI narrative for the last 3 years has been entirely focused on what machines can think. The next decade will be defined by what they can actually do in the physical world.
So just to recap the incredible journey we've taken through the source material, we are moving away from the brittle, hand-coded constraints of teach pendants, replacing them with natural language vibe coding.
Yep.
We are breaking down vertical hardware silos with horizontal software platforms, giving a shared modular brain to any robotic body. We are using spatial world models to teach these machines the laws of physics safely inside simulations.
Yeah.
And finally, we are plugging these embodied agents directly into digital workflows, effectively turning the physical world into an extension of enterprise software.
That sums it up perfectly. And, for anyone listening who is actively building this future, the author closes the article with a very specific invitation.
Oh, right, the Pegasus program.
Yes. The Microsoft for Startups Pegasus program is actively looking to back Tier 1, venture-backed physical AI startups that are building on Azure. They are specifically hunting for the companies building these horizontal intelligence layers, the advanced simulation environments, and the spatial world models that will accelerate this exact future.
It's essentially an open call to help reshape the global economy. But before we wrap up today's deep dive, I want to leave you, the listener, with a final thought to mull over. The text explicitly points out that while this revolution starts in structured environments like factories and warehouses, it is inevitably going to move into our homes.
It's only a matter of time.
So picture this scenario 10 years from now. You have a digital ecosystem managing your life. Your home software system detects a slow water leak under your kitchen sink.
Happens all the time.
Right. That digital agent coordinates with a physical agent, a general-purpose household robot. It orders the necessary replacement pipe, and while you are fast asleep, the robot goes under the sink, evaluates the spatial geometry of the plumbing, and fixes the leak.
All on its own.
All of this happens without a single prompt, alarm, or midnight panic attack from you. It brings us back to where we started. That massive gap between what AI can do on a screen and what it can do in the real world. As that gap closes, if our physical chores, both industrial and domestic, are entirely decoupled from our own human effort, what will it actually mean to manage a household or do a hard day's work a decade from now? Something to think about.